Good afternoon, everyone. My name is Michael Rinaldi, and I'm a master's student at Ryerson University's Center for Near-Net Shape Processing and Materials. I would like to thank my supervisor, Dr. Ravi Ravindran, and all the CNPM team members for help with my project on the grain refinement of AZ91 magnesium alloy with a novel aluminum-carbon inoculant. Magnesium is the lightest structural metal and can be used in lightweighting initiatives to decrease fuel consumption if parts in automobiles and aircraft made from heavier alloys can be replaced by parts made from magnesium and its alloys. This can only be possible if all alloys have similar mechanical properties. Unfortunately, magnesium alloys have lower mechanical properties that need to be improved. One way to do so is through grain refinement, but aluminum-bearing magnesium alloys currently do not have a dependable grain refiner. So the objective of this work was to improve the mechanical properties through grain refinement using carbon. Grain refinement helps increase mechanical properties from several different methods. One by distributing brittle secondary phases, by distributing and isolating porosity, by increasing isotropy, and by changing the fracture mode as well. However, the main reason why we attribute grain size reduction to strengthening is because of the buildup of dislocations at the grain boundary, which leads to an increase in yield strength as shown by the Al8Mn5 equation. This is demonstrated by the animation on the right side of your screen. Carbon can help reduce grain size by forming Al4C3 or aluminum carbide in aluminum-bearing magnesium alloys. This compound has been modeled recently and in the past to be a potent nucleation site for alpha magnesium. With more nucleation sites, there will be many more grains at the end of solidification. When comparing castings of the same volume, for example, one of AZ91E and one of AZ91E with carbon, the latter should have smaller grains and a larger grain boundary area. In my experiments, I used a novel sintering operation where I mixed ground graphite and aluminum powders in a planetary ball mill. I compacted them at a low pressure of 29 megapascals and sintered them at 600 degrees Celsius for 2 hours in an inert atmosphere. Compaction pressures are usually upwards of 100 megapascals, whereas sintering can occur at temperatures of up to 1100 degrees Celsius. Figure 3 shows the cylindrical inoculant and the mounted press used to compact it, as well as the planetary ball mill. I then added the inoculant to the AZ91E magnesium alloy melt and held it at 750 degrees before pouring it at 720 degrees in an ASTM standard cylindrical tensile bar mold. This mold was heated to 350 degrees Celsius to ensure high thermal undercooling and to form the smallest grain size possible in the final castings. The resulting mechanical properties showed improvement as more carbon was added, up to a maximum at 0.2 weight% carbon addition. Improvements were seen in UTS and in percent elongation. Grain size was reduced and grain shape changed from a quasi-equiax shape to a more fully equiax shape. However, after initial carbon addition, there was no further decrease in size as more carbon was added. This trend is reflected in the yield strength, as it did not change with increasing carbon addition. This can be explained through the Al8Mn5 relationship shown in slide 3. SEM analysis helped show that duplex nucleation started the solidification process. From the line scan results shown in figures 9 and 10, it can be seen that carbon segregated towards the aluminum-manganese secondary phase, as defined here by the darker carbon phase behind the lighter aluminum-manganese secondary phase, as well as the matching of peaks of carbon to the peaks of aluminum and manganese in figure 10. Fracture remained unchanged between all the castings. Even in the most ductile samples, mixed mode fracture prevailed, especially with certain brittle areas being characterized by spectras 15, 16, and 19. These spectra represent the beta magnesium secondary phase. Chemically known as Mg17AO12, this phase has been said in literature to be brittle, both by CNPM team members and by other researchers working on this sort of alloy throughout the world. Therefore, it can be said that duplex nucleation occurred, which grain refined the melt. Al4C3 nucleated Al8Mn5, and together, this coupling nucleated the alpha magnesium matrix. This was enabled through the addition of a novel aluminum carbon inoculant, and this grain refinement led to the improvement of mechanical properties through non-Al8Mn5 mechanisms. I want to thank everyone for taking the time to view my presentation and learn about MgAl alloys and the grain refinement efforts that are currently happening with regards to them. I hope you did learn something and that you're all staying safe and that you have a great day. Thank you very much, and take care.